Thank you. A smooth projective curve of genus G. And everything will be over the complex numbers. Okay? And so let's fix a vector bundle on C of rank R and some degree. We're not even going to specify it. So the object we're going to consider is the following. It's I will denote it in this manner, quote C. Well, at least initially when I define it, then it will be sloppier. V and D. So this is the moduli space of quotients of V. Let's call them F. Of rank N. It's in the notation, and degree D. And there's a kernel. So these are exact sequences on the curve C. And here, while the kernel is locally free, so it's a vector bundle because it's a subsheaf of a locally free sheaf on a smooth curve. This F is just a coherent sheaf, so it might not be torsion free. Okay, so it's not necessarily locally free. Yeah, so this. This moduli space is a projective scheme, and it comes with a universal sequence. So there's a tautological sequence which I will, well, this is on the Quot scheme. As you see, I'm already dropping the notation here because it will be times C. No? So it's tautological in the sense that if I restrict to a point a short exact sequence times the curve, I recover this tautological sequence restricts to that point, which I'm representing in the Quot scheme. And so this, of course, was constructed. It's a very old. This is the ancestor of all moduli spaces. Every moduli space in algebraic geometry arises somehow from the Quot scheme as a GIT quotient. Usually, so in any case, was constructed by Grothendieck. Around 1960. And so, but we're studying a very simple instance because we're working over a curve, not a higher dimensional variety. The most basic point is when you work over a point and then you have just the Grassmannian. That's the Grassmannian. All right, so now with the Quot scheme, I can distinguish two situations here. One is when the rank of the quotient is positive, so let's say at least 1. And another one when it's actually 0. So when the rank of the quotient is positive, so you could have, say, a vector bundle of a certain rank n as a quotient, then indeed, it makes sense to look at. It's geometrically significant to look at the open subscheme in the Quot scheme where this F is actually locally free. Okay, so we have that. The Quot scheme. And here, let me make the simplifying assumption that this V is actually the trivial bundle on the curve. Okay? Let's say that. In general, the exact nature of V will not play a role in what I have to say. But so then you have the following situation that this contains this open subscheme of locally free quotients. So the generic situation is truly that the quotient is locally free. Well, but that sits as a quasi-projective scheme in here. This is, but to obtain a projective moduli space, you have to allow this F to have singularities to acquire torsion. But in any case, when you do this part here can be identified. So here we're in the case when n is greater than 0. Yeah? That's what we're saying, when the quotient has rank, a positive rank. Well, this is the same as the space of maps from the curve to the Grassmannian of n-dimensional quotients of CR. Yeah, so, and this is of degree d. Yeah? So in other words, if you have a short exact sequence, of vector bundles, where this v is actually trivial in the middle, we're taking it trivial, on the curve, well, that means that at every point of the curve, if you look fiber-wise, you have a point in this Grassmannian. So overall, you create as you vary the points on the curve, you create a morphism to the Grassmannian. Okay, and vice versa. So you can identify it as such. So this is in fact the space of maps of degree d from C to the Grassmannian. So then you can think of the quotient of the quote scheme as compactifying this space. Okay, so you might want to study problems related to the enumeration of maps from the curve to the Grassmannian, and then the quote scheme is sort of a natural way to do it because it compactifies this space. And in fact, this was a point taken early on when people were studying at the beginning of Gromov-Witten theory in the 1990s. This is the school of Aaron Bertram. Well, they used the quote scheme. So this is the 1990s. Was used to study, for example, the quantum cohomology of the Grassmannian. And in fact, other questions, various enumerative questions, for example, to study various counts of maps from the curve to the Grassmannian subject to various incidence conditions. And early on, I also did some work on this with my collaborator, Drago Chopra. There were other people who worked on this, Chocan Fontanin, and so on. So, and actually, very recently, this is coming back in the sense that, for example, the quantum K theory of the Grassmannian has been reinvigorated recently by approaching it from the point of view of the quote scheme. But so let me just, before I leave this, because I don't actually want to talk about this, but I just want to quickly explain that as a compactification, so typically when in the study of this space of maps from C to the Grassmannian, there's the Kontsevich-Manin space, yeah? So you have two notions here. You have this Kontsevich-Manin space, where basically what happens is that, yes, you look at maps from a curve. Here's the Grassmannian. And in order to get a compact space, you have to allow to degenerate the domain. Yeah, so this is your smooth curve, but well, you have to, in this compactification, you allow, in a certain prescribed way, you allow the domain to degenerate. But you always have an honest map. This moduli space parameterizes honest maps. With the quote scheme, if I think of it as a compactification of the space of maps to the Grassmannian, you keep the curve fixed, you never degenerate the curve. What happens is you degenerate the sheaf. Yeah, you allow, now I erase it because the board is small, but in other words, the quote scheme doesn't parameterize only locally free quotients. Yeah? So basically in one version, in one compactification, you degenerate the domain curve. This is the Kontsevich-Manin. And in the quote scheme, the one I'm talking about, you degenerate the sheaf. Yeah? So you allow, you don't have a genuine short exact sequence of vector bundles on whatever curve, domain curve you have, but rather the quotient may be just a coherent sheaf with some torsion. Okay? And now the last thing I want to say about is that there's a rich theory of Wahl crossing between these compactifications. In the Kontsevich-Manin space of stable maps. And this is the work about 10 years old of Chokan, Fontanin, and Kim, mostly. And this is the theory of quasi-maps, okay? Okay, so there's actually, you can study how invariants change as you change the compactification. Okay, so this is the case when n is greater than 0. But in fact, today, for the remaining time, I will talk about a situation when n is equal to 0. So unless there are any questions in this sort of, I just wanted to put the space in perspective a bit, because it's a space which was studied a lot, but I'm not going to go into any enumerative direction for maps to the Grassmannian. So, okay, so let me. Well, I mean is that you can interpolate between. So there's a there's a stability condition, no? And as the stability varies, you start with the Kontsevich-Manin space and gradually end up with a Quot scheme at the other end. And then there are, of course, what's difficult is to track the change of the invariants. These are the Wahl crossing. These are fantastic hard papers by Chokan, Fontanin, and Kim from about 10 years ago. It's amazing work. You know, they allow the curve to vary. Now I'm doing this because I actually want to fix the curve, but you're really looking at a fiber over, yeah, so good point. But you can look at this version when the curve is fixed. That still makes sense. Okay. Well, I'll erase everything then, because space is at the premium here. So our setting is simpler, no? So what I'm looking at now, and I'm just going to denote it by quote dv. So this is the second case, and the one that concerns us. This is when we're looking at short exact sequences on the curve C, okay, where this f has rank 0. So it's basically, it's supported at points, okay? So it has rank 0 and degree d. Yeah? So generically, this f might look like this. Might be a sum of skyscraper sheaves. You know? That's how you should imagine it. But of course, the points can collide. I mean, the scheme structure can be, this sheaf may have, of course, a more complicated structure. But for example, when the points, it can look like this with the points distinct. So why study this? Well, you know, in some sense, this is a higher rank generalization of the symmetric product of the curve, right? Because if V has rank 1, here we get the symmetric product. We get a symmetric product of C. Yeah? Right, and well, in general, of course, so this is a higher rank version of the symmetric product, and what is the dimension? We can sort of calculate it by hand, yeah? So it's a smooth projective variety, I should say, in this case. It's easy to see, I'm not gonna argue it, but it's a smooth projective variety. And, you know, let's count the moduli, right? So if I'm thinking of this point, what I have is I have to map from V, for example, to a structure sheaf at a point. And that has, well, rank of V is R. Yeah, so that has R minus 1 moduli, because I'm looking at the projectivization of maps from just V to C. Okay, so, and I have to do this T, so R minus 1. If I just map V to the structure sheaf of, just to the torsion, the skyscraper sheaf at a point. But now I have d such points, so I have to multiply by d. And then the points are allowed to obviously move on the curve, so I have to add d more. Each point moves. So in fact, the dimension is r times d. One can argue, of course, better than I did. This is just for intuition. Okay. Well, and because this E has high rank, it's a rank R. This is a rank R vector bundle. This space historically was important in, there were connections to the moduli space of stable bundles of rank R on the curve. Certain things on the moduli space were calculated via this Quot scheme, and namely the Betti numbers, in fact. So it's a non-trivial space. But what I wanted to discuss today is something about its cohomology and also its derived category, if time allows.
So if you allow V to vary, then you get something like a relative moduli space of parabolic functions.
Yes. If I allow V to vary in some, well, I don't know, in some bounded family of sorts. Yeah, you can. Yeah, that's right. No, this does occur. Relative Quot schemes like this do occur. Yeah. Okay, so, well, what I wanted to put up the Poincaré polynomial, maybe Anderson, do you mind? Sorry, I wrote a couple of very primitive slides, and at the last minute. Oh, okay, you can't really see it. Huh? Oh, yeah, okay. So I'm interested in the cohomology, and the way to do it is to look at all degrees, yeah? So I consider all degrees at once of this F. And by the way, when the degree is 0, the space is just a point, right? So it all starts with a point. So if I'm looking at Quot 0, there's just V mapping to V, and that there's no isomorphically, yeah? So Quot 0 is a point here. And then, it starts to build up, and we'll look at this a little bit. But in any case, here is, you see this T keeps track of the degree of the Quot scheme, and then I have the Poincaré polynomial of each one, which is, with a variable z, yeah, so you count the dimension of the cohomology of each individual one. And here is the beautiful formula you have. Oh, I guess I also have a pointer somewhere, Oh, no. No. Sorry. Okay, no worries with the pointer. To press the top. I did, but it seemed to. Okay. All right. Okay. Thanks. Yeah. So you see, it's a product of very similar expressions. A product with R factors. So you see this product goes from 0 to R minus 1. It's a very beautiful compact formula. A formula which is was studied already in the 80s. So by Ströme, Gione Letizia, by Linda Chen. So this formula was known. And you see, when R is equal to 1, then there's just this rational function. And that's, you recover the Poincaré polynomial of the symmetric product of a curve, yeah? And you can see the cohomology of the curve play up. In the numerator, you have the 2G odd classes, and in the denominator, you have the codimension, the degree 0 and the degree 2 cohomology classes. In any case, yeah. So basically, I'd like to give to sort of lift this numerical result to the level of cohomology in the sense of actually understanding the cohomology groups. Yeah, and this is what follows now is some work done with Andrei Negutz. And so let me just say that, so we'll define a system of sort of raising operators that move us from Quot 0, which is just a point, to higher degrees. And so the important object to consider here is the nested quote scheme. So here is what we're going to do. So we're looking at, I'm going to denote it by QDD plus 1. Well, so this is a double inclusion, yeah? So we have V and this subshift E. And the co-kernel, I'm sorry, so then the quotient is supported at, has degree D. And then here we're going to consider a subshift of E, okay? And the idea is that E here, E mod E prime, is a skyscraper shift at some point P on the curve for P on C. Yeah? Whereas the degree of F, which is V mod E, is D. Okay. Right. So this is called a nested quote scheme, and it admits some natural maps. Yeah. So we'll examine its geometry a little bit. So there's a map where I forget this deeper sheaf E prime. So in other words, I map just to E. So I just map to E in V. So this gives me QD. Then you can also forget the middle sheaf. Let me call this P plus. And you map to E prime in V. Well, but that's a point in QD plus 1. Okay. And finally, you can remember the support point, this P. Yeah, so, and this is, let me call this PC. This maps to C. You remember the support of E mod E prime. Okay? You agree? So that's sort of just very basic things we could do, but it allows us to form an impression of this nested quote scheme, because I want to analyze it from the point of view of this fibration, P minus. So you see what lies over a point in the quote scheme. So how, if I start with E in V, how do I end up with an E prime? Well, that's particularly simple. So given E in V, so I'm looking over a point in QD, what is the fiber of P minus 1? Well, I have to choose, it is enough to choose just a morphism from E, a point on the curve C, and then a morphism to the skyscraper sheaf of E. And the kernel of this morphism, oh, and I'm writing this terribly. Oh. Let me put it like this. CP. And the kernel, of course, in V, no? To get this E prime, I just have to choose a morphism from E to the skyscraper sheaf. So overall, what I do is simply projectivize the universal bundle, no? So in fact, if I'm looking at the projectivization of the universal bundle over the quote scheme, this is, so this is quote D cross C, and this is the map P minus times PC, so you map to, well, this is, in fact, this is the nested quote scheme. So it has the structure of just a projective bundle. So what, if I nest to degree D plus 1, just a projective bundle over quote D times the curve. Okay, so yeah, any questions about this? It's kind of a basic point for us. It will be useful too. So in particular, what dimension does it have? Well, we can calculate. Now, this has dimension RD plus 1, and the projective bundle has rank, this is a fibration of rank R minus 1 because E has rank R. So has dimension R times D plus 1, and obviously it's also smooth, no? Because it's over a smooth base. So this nested Quot scheme is a very beautiful thing. Now, with this P plus, what is the structure of this fibration? Well, first of all, these are smooth projective varieties of the same dimension. No, this has dimension r times d plus 1. This is dimension r times d plus 1. Well, how do I do if I start with E prime a deeper sheaf, such that the quotient V mod E prime has degree d plus 1? How do I recover this E in the middle? Well, so generically, you see, if the quotient is, and you should picture what you try to understand, it's just the simplest possible scenario. So I picture a quotient which is, as I said, a sum of skyscraper sheaves. And so what I need to do to get an E is choose one of the skyscraper sheaves and leave it out. Yeah, so then if I choose any morphism to, let's say I leave out P1. Yeah, so this is from I1 to D plus 1. Yeah? And then I map to C, P2. Okay. Well, so then the kernel of this, yeah, so now I have a surjection from V, not just to F, but to this smaller sheaf, if you want, and the kernel will be exactly this E. So then, in fact, generically, this is a degree, it depends on what point I choose, yeah? So generically, this will be a D plus 1. So if I'm looking at pi plus, from quote d plus 1 to d quote d plus 1, this is generically finite of degree d plus 1. Now, of course, however, to do calculations with this P plus is more complicated. P minus is sort of beautiful projective bundle structure. P plus, which is the direction in which you want to move from lower degree to higher degree, is actually complicated. But the main point here, which I will not actually have time to explain in detail, but it's rather important, is that in some sense P plus is also a projective bundle over this, but a projective bundle of a virtual bundle, in a sense of a bundle of a virtual bundle of rank 0. Yeah, so there's a way to make sense of it also in this projective bundle picture, but in a more subtle sense than for P minus. Okay, so yeah, I need that, but this diagram is rather important for us. And no, because if the, right, so what might, obviously when you have a different quotient structure, this might, you might have a positive dimensional fiber, no? So, yeah. So generically, this is the picture, but again, this is not a simple map, precisely because not all points are, not all quotients are of this form, yeah? But it gives you some idea. Okay. So, yeah, maybe I'll leave that. Yeah, so now I'm going to define this operator. So if we have this, we use this understanding of the nested Quot scheme as a projective bundle. So then on the nested Quot scheme, there's an exact sequence which every projective bundle has. This is a kernel. This is the pullback of the universal sheaf. And then we have the hyperplane, yeah? And again, this is just because it's a projectivization of this E, of the universal sheaf, on quote D. I'm going to use QD for simplicity, D plus 1. Okay. So let's say that, it's hyperplane bundle. Let's say that we are naming its first Chern class lambda. Okay. And then Right, so here are the creation and annihilation operators. So here, maybe it's soon, I will write them, but then I think I also put them on the, but it's good to have this board. So here's where we're going to define the following collection. We're going to define operators EK, which go from the cohomology of quote D to the cohomology of quote D plus 1 times the curve C. Then we're going to define reverse operators that go from the cohomology of the co-scheme of degree D plus 1 in the other direction, the cohomology of co-scheme of degree D times C. And finally, we're going to define some operators which keep the degree. So you move from the co-scheme of degree D to the co-scheme of degree D. I'm sorry, it's QD times C, that's correct, yeah, sorry. Yeah, thank you. Right, so we're gonna define these operators and how, well, I have the maps, I don't know what to erase. Maybe I should move with this, because I put them there also on the slide, I think. Okay. You see, so what you do is, well, you take a class alpha in the cohomology of quote D. You lift it, so you lift it via P minus to the nested structure. But there you have naturally this hyperplane class, yeah, because the nested co-scheme is a projective bundle. So I take a power of the hyperplane class, which is what index is, the kth power. This index is my operator. And then you project via P plus times PC to QD plus 1 times C, okay? And for F, you do the reverse. You start with a class in the cohomology of QD plus 1, lift it to the nested co-scheme, intersect with the power of the hyperplane, and push it down to a QD minus 1. And what about this M? M is something, it's just multiplication by the universal Chern classes of this. There's a universal bundle, and you just send, essentially here, you just send alpha to the kth Chern class of V times alpha of the universal, where you view this alpha on the product. You pull it back to the product, and this only goes, these go for all k. These you can allow all k greater than 0, but this mk, because there are only R Chern classes, this goes from between 0 and R, okay, because E has a rank R. Okay, so you do this and you hope for the best, and you know what you might hope is that this, when you compose, now the question is what happens if I compose, if I have form a string of these E operators? Well, the problem is they don't commute. Okay, so in fact, let me see if I wrote a, also take a look at I'm not sure how we're doing with time. It's actually okay. Yeah. We started at 10:30 or 10:25. Okay, yeah, that's good. Yeah, so the operators don't commute, but in fact, I can tell you, now I can erase this basic diagram. Or maybe I leave the basic diagram. I erase this stuff. The basic diagram is good to sort of yeah, so here is the flavor of commutation relation you get. So in other words, what does it mean? Obviously you can compose these operators. So I can look at EK composed with EL, and this will be an operator I can pick it up in any D. Quote D to, at this point it's quote D plus 2, because I moved 2, the degree by 2, times C. Yeah, so this is, the composition has this effect, that it pushes you further. But and then you can consider commutators, and as a remark, you see the following, that you have the following commutator. I'll just write, it's not important to obviously remember this exactly, but it gives you a sense of what, just to impressionistically to look at it. E-L-E-K. Sorry, this is, yeah, so you see it's kind of complicated. There's an obvious relation, and this delta, what does this delta mean? This is delta, this is diagonal in C times C pulled back. Yeah, so it's multiplication by this. So whatever you get by doing this subtraction lies over the diagonal in C times C. Okay, so that's, but what the main point, one of the nice things about the whole structure is that something does commute. But it's not these operators E which I defined. So I'll define one more class of operators. And it turns out, and I'm going to call them AK. So this again goes from the cohomology of Quot D to the cohomology of Quot D plus 1 times C. And here what you do is the following. You send the class alpha. I didn't write it on the slide, in fact, but you send the class alpha in the cohomology of the Quot scheme. Well, you lift it via P minus to the nested Quot scheme. And what do you intersect with? You don't intersect with the power of a hyperplane, but you intersect with the Chern class of this rank R minus 1 subbundle in the tautological sequence of the projective bundle. And then you push forward. So it's this. So it's P plus times, so we push forward of the pullback of alpha intersected with CK of this G. Yeah? So up on QDD plus 1, you intersect with this beautiful Chern class. And now the miracle happens that these operators do commute. Yeah, so, and so then the theorem is, well, I'm going to erase this basic diagram now, okay? So, well, it comes in two parts. Let's say part one is this basic fact that, that AK composed with AL is equal to AL composed with AK. Again, moving from Quot, from any D here. You can pick it up at any D, but you displace it by 2. Quot D plus 2 times C, sorry. Well, then the second part is that, of course, you can form a string of these operators. And then the basic result is that the entire cohomology of the Quot scheme so for D greater than or equal to 0, and this is with Q coefficients, okay? I didn't specify, but is obtained by applying these strings of operators, which you order, let's say, from higher to lower. Yeah, so now you can, since they commute, you can always push it to the, so here is, and you need D, right? You're gonna start from 0, and 0, Quot 0 is just a point. And we're gonna call it fundamental class. I'll explain the notation in a second. 0, okay, it's a vacuum. We're gonna call it the vacuum of our cohomology system. This is the fundamental class of Q0, of Quot 0. Okay, and this sum goes over, with strings, ordered strings like this. KD greater than or equal to 0, and it goes up to R minus 1, okay? because this bundle has rank R minus 1. Oh, yeah, I think, okay, this R minus 1. No, it's 1 less pi. Okay, and what is this gamma? Well, gamma moves in a Q basis. I'll explain in a second how we form this. I should have explained something before, but I'll explain it now. Right, so basically here you take the invariant, or maybe, maybe let me put it like this. A basis for invariant classes under the action of this partial symmetric group, which you get because some of these operators might be the same. Okay, but let me explain first how I think of this, now with this, what does this notation mean? Well, the way I define things, let me just explain what I wrote here on the right. So what this string is, AK1 up to AKD, so I have D operators in succession. Well, these move you from the cohomology of, the way I view it, of 0 to the cohomology of the coscheme of degree D times C times C times C D times. Yeah, because every time you apply an operator, you also get a copy of C. Hey, but this, here you just apply this to the only class you can apply it to, the fundamental class, this 0. So a priori you end up in this thing, but now what you do is you pull back a class from the symmetric product, and then intersect with the image of 0, and then push forward to quote D. Yeah, so the string of operator moves you, gives you there. So it gives you so in particular AK1, AKD 0 is just a point in the cohomology of quote D times C. Okay, well, but you want to end up actually in the cohomology of quote D. So you intersect a class gamma coming from the self-product of the curve with this class, and you push forward to quote D. Okay. So you basically here this, I'm sorry, I'm here in this murky territory here. Yeah, so I want to end up in the cohomology of quote D. So this is gamma intersected with this A string applied to 0. And then push forward. And push forward, right, pi star. Okay, any doubt about this? It's a simple thing, okay? All right. Yeah, so you see, yeah. And this is the right thing to consider, in fact. Yeah. So if you might have, for example, you might have all operators. You might have just A0, yeah, throughout. Well, in that case, what you choose is a class in the symmetric product, CD. Yeah. So these operators might coincide. In fact, there are only R-1 distinct operators, but you have a string of D, and D goes to infinity because I consider increasing and increasing degree. So there'll be a lot of overlap here. Yeah. So I apply the same operator many times, and then I symmetrize with respect to the copies of the curve corresponding to the operators which are identical. That's what this means. It's not a big deal. Yeah, so this is the cohomology of the quote scheme, and you see if I look back at the Poincare polynomial, yeah, you can see these. You see these R, so how many operators A I have? I have exactly R from 0 to R-1. And you can sort of see it appearing here, yeah? You have this is the product in the series, and then this is the symmetric product of the curve here. So the Poincare polynomial suggests that such an algebra should act of commuting operators. And that's very similar to a simpler setup, for sure, then the situation for the Hilbert scheme of points on a surface. When Goethe calculated the Betti numbers of the Hilbert schemes, and then Nakajima and Groznovsky came up with the Heisenberg algebra action on the cohomology of the Quot scheme, of the Hilbert scheme of points on a surface. That's actually a harder setup because it's one dimension higher. Okay. And here I wrote, I'm not going to write it now but I put it on these slides, little slides. Yeah, you see, these are the operators we defined, these E's and these F's. And you can organize them to study their, well, because these A operators, it's a system of R commuting operators inside a bigger algebra. And this bigger algebra is the algebra formed by these E, F, and M. And you can organize them in some formal series of operators. You see in this sort of, so you see this E of Z. You keep track of the negative powers of Z, basically. And then you can organize the commutators in a beautiful way in terms of this series. Yeah, you write it in terms of this series. I'm just putting it on the board just to give you an impression. So for example, the commutator of E and F, which I have on that, of E and E, which I have in that remark, is the first equation here. So you multiply this series formally, and you look at the negative powers of Z and W, and when you extract the coefficients, you get exactly that. So it's a nice way of packaging all the commutators together. And this algebra is called the Youngian of SL2, in a sense. And these A's fall in as it's a commuting sub-algebra inside the larger algebra which acts. I just wanted to put it there. It's something that we sort of, it's a picture we understood in detail. But at first sight, it's best to. Well, they are. I mean, these M's are. This operator M is multiplication by the universal class. So it's all. That's precisely right. These are all. You see, so in particular, we calculate. Here you calculate the commutator of this raising operator with multiplication by the universal class. So it's a very exhaustive study. Yeah, we understand all of these things, how the nested co-scheme interacts with the universal classes, basically in great detail. And what's really used here, and of course, I'm not giving any details about the argument, but you really have to understand this P plus map. Now you have to understand what happens when you move forward. There's this virtual projective bundle structure, which is quite important for the calculations. But
and if you convert this to homological Fourier factor,
yeah, that's what I was going to say next. You can do that. That's precisely right. So let's see if I have 10. I don't know how much time I have to. 12 minutes? Yeah, it's good enough for the derived category. Yeah. It is what's there, so to speak. You should think, this is an algebra introduced, studied by Drinfeld, in fact. But so you should think of it as an algebra generated by these symbols, E, F, and M, subject to these commutators. In some sense, it's explicit like this, but it's not a Heisenberg algebra. It doesn't quite contain a Heisenberg. I'm not going to write this, but you can study the commutators of this A. I mean, you have to, in fact, to show this theorem, right, to show that this action exhausts, right? So you keep applying this string, and this exhausts the cohomology of the Quot scheme. Yeah, you need to study all the commutators, and it's not a Heisenberg. Things don't commute as nicely. It's not as perfect as the Nakajima-Groznovsky picture. That's a particularly simple algebra. This algebra is a bit more complicated, but not, okay, very, very, very understandable. No? Yeah.
It's also, it's also subject to Groznovsky's calculus.
What meaning exactly?
That you can find very particular basis.
Well, yeah, this theorem achieves a canonical basis of the cohomology of the Quot scheme. You start with 0, which is just a point. There's no choice there. You have one class. And then you apply these operators, you build in. So these are cohomology vectors, yeah? And it's completely canonical. Yeah? So yes, in that sense, it's similar. You have a Nakajima type basis. That is right, Nakajima-Grozhnovsky type basis for the cohomology of the Quot scheme. No, I mean, now here we don't have any stable maps because we're in this rank 0 situation. Yeah, so, but, yeah. Yeah, so, all right, okay, so let's, yeah, so no, Eugenia it's sort of very natural. I mean, okay, you define these operators on cohomological levels, but you can very easily consider them on the level of the K-theory or the derived category, really. And so, and then you have some nice results there, too. I didn't... And the main point is that somehow, so what you get is just the way we get this decomposition of the cohomology indexed by this data. What is the data? Well, this discrete data of the string and the cohomology of the curve, partially symmetrized. This is exactly the data that will index a decomposition of the derived category, a semi-orthogonal decomposition. The blocks will correspond to this type of data, the derived category of partially symmetrized, or products of symmetric products of curves. Yeah, so, yeah, let me state it first and then I'll try to explain it. Yeah, so well, let me put the theorem first and then I will try to exactly explain the functor, basically. But for any R string, so we're going to consider R strings of degrees. So I'll start with dr minus 1, dr minus 2, d1, d0. And these numbers sum to d. Yeah, you always have to sum to d. So the d0 plus d1 plus dr minus 1 is equal to d here. Well, there is a fully faithful functor I'm going to call it E sub d, so corresponding to this particular string. Let me call the string d. That goes from the derived category of the product of symmetric products of the curve, C dr minus 1, okay, to the derived category of quote d. And so as D ranges through all R strings, the images of these functors yield a semi-orthogonal decomposition of this. So as D varies, the images of ED give a semi-orthogonal decomposition. Of quote D, where the morphisms are allowed only in non-increasing, it's a question of ordering, lexicographic ordering of these strings. So the non-zero morphisms point in decreasing lexicographic ordering. So it's very similar to this cohomological theorem, no? Well, let me. Yes, and this is also, this we recover a result of Toda. So Toda said, well, but yeah. So this is Toda 2022. He also, or I don't know, something like that. But he's, I mean, supposedly it is up to a shift, the same decomposition, but we don't know how to show it. He's, I don't know, he's, yeah, it's a bit, his picture is more complicated. This is very geometric. It's just based on these raising functors. Yeah, so, okay, well, so, yeah, so what is this functor? Yeah, I mean, it's this notion I will sort of indirectly say. I mean, maybe I erase this here. Yeah, no. Yeah, so look, how do you construct these strings? I mean, yeah, you should think of this as follows. I mean, you start with the code scheme of a point, in degree 0, which is just a point. Now then you build over it. Let's keep this sort of, it's just a basic geometric picture here. You know, degree 1, you get degree 1 over as a projective bundle over this setup. As a projective bundle over this I'm sorry, you get quotes 0, 1. So the nested quote scheme. Now here, as a projective bundle, you can keep projectivizing this setup, and so you have this tower of projective bundles, etc. Okay? So at each step, you have a rank R-1 projective bundle over the, and so what do you end up, finally? You end up with this code scheme of full flags, you know, so, which is implicit in the operators I wrote before. It's just a slightly different phrasing of it. So this is just, you know, you have this full flag of up to degree D, you know. You start with degree 1 in V, and then you move up to degree D. You keep track at every point. So here the jump is just of degree 1. Yeah? So each of these successive quotients is supported at one point of the curve, which is why you have this, you know, this tower of projective bundles. And the tower of projective bundles, as Zhenya was pointing out in his talk, well, you understand the derived category of that, starting with basically with a point here, yeah? So you see how this maps on the one hand to CD, yeah? And then, you know, at each step, you have these hyperplane bundles, and powers of it will give you the tensoring with that will give you a semi-orthogonal decomposition in the end of this tower up to here. But this is a very beautiful space. However, it's a bit messy when you map down to quote D. And when you map up down to quote D, you forget all but the deepest sheaf in the flag. Okay? So you say, okay, I don't care how I got here. So you forget the root, and you just remember this ED. And this is a bit of a difficult map to understand. Yeah, so here you have this sort of, you know, super simple variety, this tower, you know, going on, and then you forget about the root you get, and end up with the code scheme, which is a bit harder, okay? But in any case, what you do essentially is that, you see, you get a map from the derived category of CD to the derived category of the quote scheme, quote D. Well, you know, you pull back an object from here up to the fully ordered product, and then so this is this, let me call it E sub tensor. Well, this functor. And let me just explain how you do it. Maybe I'll erase the theorem, because now this is not quite what we want, but it gives you an idea. And I think if I have one more minute, or I'm out. One, okay, yeah, one. Yeah, so Okay, so what you do with this ED, E tilde D, so you have a string. Well, you take some object in the derived category of CD. You lift it, okay, via this map. Let's call this PCD. I'm sorry, PCD. So gamma, you send it, well, you lift it. Okay. And now you're up here in this very beautiful ordered space, this tower of projective bundles. And here you tensor with the strings of tautological bundles. Since you have a D, you have a projective tower of length D. Each of them comes with its own hyperplane bundle. And these have to be ordered in a specific way, but you're going to have D of them. So you take, well, let's see how See, you take the first dr minus 1, and you raise them to the power minus r plus 1, and then you keep going like this, up until you hit d minus d0 plus 1, up to LD. You're going to have D tautological hyperplane bundles, because you have D towers. Okay, this is to the power 0. Okay, so you do this, and now, okay, I should have reserved some space. You push forward via this P plus. Let's call this P plus. This is the forgetful map that only remember the sheaf. And this is a pretty good functor. That takes you from the just the product of the curve to the co-scheme. So this is almost the functor you want. In fact, the thing is that the functor you want, you see, it has to take value. It takes you from a symmetrized version of this. But if you pull, so this ED, that is the real functor that we're interested in, composed with, I'm going to call this tau lower star, is equal to this E tilde D. And this tau is the map from the partially symmetrized, from CD to the partially symmetrized curve. Right? So you can map by just mapping, by quotienting by a product of smaller symmetry groups. You have this tau. And what you do, if you take an element in the derived category of this, you push it forward via tau, and then you apply the functor, the real functor that I haven't told you exactly what it is, you get this functor which is very explicit. Yeah? So you get a sense. You basically obtain this functor from this tensoring with suitable powers of the tautological line bundles that appear. Yeah? So yeah, I'll stop here because I'm for many reasons, but yeah, primarily I'm out of time.